Hi guys, be welcome to our first section of Curiosities Part 1. So everyone knows what is I square is equal to minus 1, I cube minus I raised to 4 equal to 1, I raised to 6 is equal to minus 1. However, what is I? That's the question, okay? Let us solve for this one, then go to the second one. So what is I? So to prove or to find what is I, we have to remember about Euler equation. Okay, see here this Euler equation. This is the equation that is making the relation between the parabola, sorry, not parabola, that between the hyperbolic trigonometry and the and the normal trigonometry. Okay, if I can say like this. So this equation, it is the base from where we found this cosine hyperbolic, sine hyperbolic, and so on and on. Now see, this is the Euler equation. With the help of Euler equation, we can find what is I directly. But the question comes, it is how? Okay? See, here we know that in Euler equation, Euler raised to ix, okay, is equal to cos of x. Then here it is like I sinus of x. So how to find my I? Now suppose I have just to put whatever I have here. Like suppose sine of x, cos of x, and here we have x. So what should be this x so that I can just keep this I alone here? Okay? So now think a bit. What should be the angle that should make this one equal to 1, okay, or equal to a number, whatever number, and should cancel this cosines. So surely the angle will be pi by 2, okay? So for x equal to pi by 2, okay? And as we know, this sinus and this cosinus has period, okay, of 2 pi. So for many periods, so I will add k. We know that this k belongs to integer number conjunction or group. So then we will just substitute in this one and this one and this one. So what should be this one? So it should be Euler. Where you find x, just substitute, will be I raised to, okay, Euler raised to I pi by 2 plus 2 k, or pi plus 2 p k, and that's equal to, here if I put this one, this will be 0 directly, and here will be 1, okay, this will be 1 directly. So then I'll get 0 plus I times 1. So it means that I will be equal to this expression, Euler raised to I, okay, pi by 2 plus 2p k. Okay, this is your I. So whenever you have this expression like I, okay, you can substitute by this expression over there. Okay, now see, it's not a kind of equation so that you can just solve by I and find what is I. Okay, I is a constant, imaginary constant number. Okay, and from there you can use and solve this one. So in what this expression should help you? Okay, sometimes we have crazy equations like crazy equation. I say crazy equation because they are really crazy. Suppose we have like I raised to I, okay? How to find I raised to I, okay? From here, you can find what is I raised to I. Knowing that I is equal to Euler raised to I, pi by 2, and so on and on, okay? You can just go and find what is I raised to I. This will be, just substitute Euler raised to I and pi by 2 plus 2pk, okay? This is raised to I. Multiply this I and this I, so I raised to I will be equal to Euler raised to minus, here will be minus, pi by 2 and plus 2kp, okay? So this is your I raised to I. And from this, also, from here, you can also find the golden equation of Euler. You know the golden identity of Euler's identity. Like, you have this one, Ix is equal to cos of x plus then I sine of x. How to find this identity over here? Like there is a Euler's identity. I will show here this one. To find Euler's identity, okay, Euler's identity, what you have to do, okay, we know, okay, that to find Euler's identity, here it is x and this one and this one. So just substitute for x equal to pi. Okay, Euler just did this one for x equal to pi directly, roughly. Okay, so for x equal to pi, forget about the period or something like that. Even here, you can just forget about the period, just put this one, this rough value, and this is fine. But see, for this one, x equal to pi, it will be Euler raised to I pi. It's equal to cos of pi plus I sine of pi. See, sine of pi will be equal to 0. But cos of pi is minus 1. Euler raised to I pi is equal to minus 1. This is what we call the golden equation of Euler. And this is Euler's identity. Okay? Here, it is combined every source or every kind of numbers. Like here, we have Euler that is irrational. Okay, Euler is irrational number because it is like infinitely, how can I say, without period. Yeah, Euler, this one. And here, pi is also an infinite number. Okay, yeah, like, how can I say for pi, it is like irrational. Okay, and here it is an imaginary number. So here we have two irrational, like two rational numbers, okay, and one imaginary number, like this one. So this is very famous Euler identity, and this is mainly or too many times used, and this is fine, okay. Now, see, after seeing this, now what about this guy, okay? What about this guy? So from Euler's equation, you can find what is I, and you can solve problems like this, okay. Sometimes you have equations, crazy equations, like suppose they ask you to find I raised to 2x, okay? I raised to 2x is equal to 3. How to find this equation? So you can apply this one, do this substitution over there, and just solve them. This will be fine. Okay, it's fine. Okay, now let's go for the last one. This exercise here, this point here. Okay. Now, how to find, how to show that this is true. This can be plus or minus infinite. See, we know that log, this is a of 0 is equal to, we don't know. We don't ever know. Okay? So how to show this one? Okay? First, we have to analyze the condition here. We know that for this base, a has to be different than 1 and a must be greater than 0. Okay? Then if you just do this intersection, so here it is 1, okay, a equal to 1. So at this point, it must be an open, okay, and it must be greater than 0. And I'll put here 0, okay. This is a equal to 0. So this is a equal to 0. What does it mean? It is like for a greater than 0, so it will be like this. So it will be like this. Okay, this is a equal to 0 at this point. Okay, this is the positive, this is the negative side of this. Just like this. Negative and positive side of this. Now check. Here they say that a is greater than 0, so it will be all of this way. So then how to solve or how to find the general solution for this one, for this case? So it means that our condition will be lying between 0 to 1, 0, a will be between 0 to 1, and, okay, and, or a will be greater than 1. These are the two, so the two conditions for this a, okay? Two conditions for this a. A will be from 0 to 1, 0 to 1, and from 1 to infinite. Now that we know this is fine. So I will solve this equation for these 2 points of view. Okay, here it is when a is greater than 1, and here it is when 0 and a and 1. Okay, I will solve for these 2 points of view, these 2 conditions. Now see, for log 0, between this interval, it will be log of 0. A is in between these 2 intervals. Okay, it means that here, this number will be less than 1. If it is less than 1, so I can just jump this on. Okay, so for this interval here, we know that this logarithm will be negative. For this interval, will be negative. Okay, it's like when you have log of a, and a is like 1 by 2 in between this interval. So when you just send this guy up, like suppose it is a, when you send this up, what you have, a here 2 minus 1, and this minus 1 will come here, so this will be minus. So this interval will will take the range of negative of this expression here. Okay, this will be negative of this expression here. So okay, this one is for log negative, and this is equal to 0. We don't know what it's equal to, but this range, okay, this in the opposite side, here a is greater than 1, so it means that here it will be positive, like greater than 1. It can be 1.2, 2, 3, 4, 5, so it is positive. Okay, so here I can write like a log in base a will be positive. Okay, this log will be positive. This is positive domain, and here it is negative domain. Just easily. Now see how to find this and how to find this. Okay, now see here, log of this guy. So log, okay, of 0. We know what is 0. 0 is 1 upon a. Now I can just write here 1 upon a. So what should be your a so that this 0 can be, this expression can be equal to 0? That's the point. Okay, what should be your a so that this expression can be 0? So we know 1 upon a, if this number here is in between, okay, 0 and 1, and I make it raised to infinite, what will it be? Okay, if this number here is infinite, and I make it like infinite. Suppose it is 1 by 2, and it is raised to infinite. What should it be? That's the point. So it should be equal to 0 directly. That should be equal to 0. This expression here, when I put here to infinite, this will be equal to 0. And that, okay, this expression only, and that will make sense for this one. Okay? Yeah. As we know, a here is in between this space, so it means that a raised to infinite is equal to 0. Okay? Yeah, because this one is in this way. So, okay, we can just write log, where we have 0, I will put a raised to infinite. Okay? And here it is a. What will it be? That's the question. I don't know. Okay? Yeah. A raised to infinite again. 0 to a to 1. So if I put a raised to infinite, it will be 0. Because a is in between 0 to 1, that is less than 1 and greater than 0. Now just substitute this one. This will be equal to 0. This is the same. This is fine. Now just prove. This is infinite. Just come here. This will be infinite time log of a in base a. And that will be equal to infinite time 1. And that's equal to infinite. You see, this is equal to infinite, positive infinite, positive infinite, positive infinite. Okay? This is one just like this. Positive infinite and positive infinite. Okay? This is true. So it is proved. Okay? Infinite is equal to infinite. So it means that log of 0 in a is equal to infinite only if this a is in between, okay? A is in between 1 and 0. Nice. Now, let us check for this positive part. So this one is a positive part. So whenever we just make this a raised to infinite, this will be equal to infinite because this a is greater than 1. For a greater than 1, a raised to infinite is infinite. So now how to prove this one? So this one will be equal to log of, we know that every number 1 upon infinite is 0. So we can just put here 1 upon a raised to infinite, okay? And here a, it's equal to, we don't know, we want to know, okay? Is this true? Yes, it is true because a is greater than 1, a is greater than 1, and a raised to infinite is 0. So a raised to infinite is infinite. So 1 upon infinite is 0. I'll come back here. Now see, this expression, I can just climb it up. I'll get log of a raised to minus infinite and a here. So this minus come here, I'll get minus time log of a and a. Okay, so here directly you can see minus infinite times 1. And here you can get minus infinite is equal to minus infinite. Then it should be minus infinite, minus infinite, minus infinite, minus infinite, minus infinite. And this is proved. Okay, this is proved. Barely. Okay, so what we can say that log of 0 in the base a equal to minus infinite only when a is greater than 1. Okay, it's greater than 1. Nice. Yeah, and it is done. So really it is proved that log of 0 in the base a is equal to, can be either plus infinite or minus infinite. Okay, just like this, plus minus infinite. Done. Thank you. See you in the next lecture. And let me give you a bonus, kind of bonus. Like, do you know? I don't know if you know or if you are acquainted, but let me just add just one more curiosity like about. I don't know if you know, but let us see. Okay, let's see. You know how to prove this integration here, like Euler raised to ax time cos of 2x, bx dx, or integration like Euler raised to ax sinus of bx dx. Okay, just how to prove this one, how to solve this one. I have a short, quick method to do this one, and I call this method DI, okay? Derivative integration method. Okay, the same you will do with this is the same that you'll do with this one. Usually you will see in the books, this is written like, when you have this expression, it will be equal to Euler raised to ax upon a squared plus b squared, then time, okay, time, and what else? I just forgot. But anyway, this will be b sinus x, b sinus bx minus a cosinus bx. Okay, and for this one, it's given like this: Euler raised to ax upon a square plus b square. Then here it is the same, like they will just b sinus of bx plus a cosinus of bx. But you know, I don't know if I'm right or not. So I will solve for this one, okay, and that for that one, and that will be easy. I will solve for one, and you will have to prove for that one, okay? Now see, when we have this expression, suppose I will solve for this is 1 and this is 2. When I have this expression, how to solve this expression? That's the point. Just I will apply DI method, derivative and integration method. Derivative, here you will put the function that is easy to derive, and here you will put the function that is easy to integrate. Now see, here Euler raised to ax is a function that can be either easy to integrate or derived, or to apply derivative. And sinus bx is also easy to integrate and to apply derivative. See, when you have Euler of x, Euler raised to x, and sinus, these are called like cyclic function. And cyclic function, it means that this function, at some point, okay, of this integration of derivative, they will repeat each other again and again and again. Okay, so that means that here, even if you change, put this one here or put this one here, this will be the same because both derivative and integration of these two functions are cyclic. So if I put here Euler raised to ax and here integration of sine x dx, so what will it be? I will just derive this one till I get this expression, this combination, Euler raised to ax and sine bx in parallel side, like straight. Okay, here I will put this one and this one. So sine x derivative or integration of sine x will be what? I will do simultaneously. Okay, integration of sine x, it is what? Minus cos x. And derivative of Euler raised to ax will be a Euler raised to ax. Again, I will do derivative and integration. If I integrate this sinus or this cosinus, will be sinus of x. Then if I derive this one, will be a square Euler raised to ax. Okay, are we together? Now check. Do we have, see, Euler raised to ax, and this is the equation. Nice. Now here you have this expression is repeated. Check, this expression is repeated, and here we have again sine of bx. Okay, sine of x. I called sine. Oh, whoa, sorry. It's no problem at all. I have just to put b. Okay, 1 upon b, and here 1 upon b square. Because here it is bx and it is bx. Okay, no problem. See, as I was saying, if you put like this is 1 upon b, 1 upon bs, b square. So if you see here Euler raised to ax and sinus bx. This is the same. These guys are the same. Okay, as I told you, they will repeat sometimes. Okay, they are cyclic. So they at some point of this derivative and this integration will meet, and they will be the same as the first integration. Now at that point we will solve this one. So now what's the next step? Just join these two and join these two also. This is plus, this is negative. Okay, then as we found that these guys are the same as my main equation, as my main integration, so I will multiply them in the third place. So what does it mean? It means that if I have this expression, I'm solving for these two here. If I have Euler raised to ax sinus bx dx, it will be equal to this times this. This times this, plus and minus, minus this times this will be Euler raised to ax, negative here, time cos bx all upon b. Then this guy times this, minus and minus, positive, plus a Euler ax time sinus bx all upon b square. Now I will multiply this and this. That will be, okay, that will be what? If you check, this will be minus a square upon b square integration of sine x, sine bx times Euler ax dx. See, yeah, in this way, just see, this expression is equal to this one. You just can come this and come here. This will be what? A, b, okay, square, plus 1. Integration of Euler ax, and here sine of bx dx. Here it will be, this is minus. Just find the common denominator here. Okay, it will be what? That will be a Euler ax sinus bx minus b cos b Euler ax, okay, cos bx all upon b squared. Okay, just like this. And then you just have to just solve this combination here. If you just solve this one, this will be b squared upon, this will be plus b squared all upon b squared. Now, this expression and this one will be cancelled out, and this one will go down. So Euler raised to ax times sine of bx dx will be equal to, okay, just factorize this one, Euler raised to ax all upon a square plus b square. Okay, wow, it's gaining shape like, okay, and then here, okay, this is a, with sinus it is a. Okay, now I'm seeing where I made the mistake. You see, where is the mistake in that formula? Yeah, that's why I don't like to memorize a lot. But actually I did it on purpose, okay? Now see, as you can see here, this is linked to I, so yeah. See here it is A, then sinus, and so on and on. So it means that here I will get this and this. This is Euler. I'll get A sinus of bx, okay? Then minus B cosinus of bx. Okay? If you see this, okay? Yeah, it means that this is the problem of memorizing too many things, right? Yeah, that's why I don't like memorizing, really. Okay? Okay, so it means that here I have to change, it's A, and it is B. Okay? I don't know, let me see this one, sine of bx. I just have to check, okay, whether there is a mistake or not. Just like this one, it's negative, right? It's okay. This is negative. This and this, it's negative. And this, okay? When we integrate cosinus, again, if I integrate cosinus will be, yeah, negative. Yeah, that's it. Yeah, that's it. That's it. So plus, minus, here will be positive, this will be negative. Yeah, and that's it. That's it. That's it. So from here you can just then solve them. Yeah, cosinus negative and sinus positive. And this is the way. Now see, for suppose you have here cosinus. I guess here for cosinus, just try to solve it home. It will be positive over there. Okay? For cosinus, it will be positive here, over there. I will just do a quick hint on this. Let me just show this one. Okay? Just a quick hint on cosinus. What will it be if it is cosinus? That's the point. See, if it is cosinus, I will put here. I can change. Cosinus can come here. I'm solving for this one now, from the first. Cosine of bx, and here Euler of ax dx. Cosinus derivative, it is minus sine of bx. In this case, minus b. Okay, minus b, sine of this one. So integration of this guy will be Euler raised to ax all upon a. Now I apply derivative again. It will be minus b square, okay, then cosinus of bx. Apply integration again, okay. I integrate this one again. It will be Euler raised to ax all upon a square. Now see, at this point, this guy and this guy are the same, okay. Euler raised to ax, okay, upon a square. At this point, these guys are the same, so I have to stop here. Okay, these guys are equal to these guys. To this guy. Euler raised to ax cos bx. Euler raised to ax cos bx. So I have to stop. It means that I have just to multiply them. Yeah. Then multiply this and this for positive one, and this for negative side. Okay, now what will it be? So now see, what will it be? It will be this integration here, Euler raised to ax cos of bx dx. This will be equal to this times this, okay, cos of bx times Euler ax all upon a. Okay, then minus and minus will be positive. This will be